Good afternoon, everyone. Welcome to today's edition of NSF Colloquium. It's a pleasure to have Professor Dibyendu Nandi from IISER Kolkata as our colloquium speaker today. A few words about his research trajectory, just to get you introduced to him. Dibyendu did his PhD from Indian Institute of Science in Bangalore, and he went on to do his postdoc in Montana State University in Boston. He returned to India in 2008 and has been with IISER Kolkata since. Dibyendu's research interests are in the area of MHD, magnetohydrodynamics. He has worked on sun and plasma, generally magnetized plasma, generally. So I'll invite Dibyendu to give this colloquium titled Stellar Magnetism and Life.
Thank you, Manoj. It's a privilege to be here at TIFR talking to you. Can I see a show of hands of people who are non-astro people? Can I just see it? Yeah, great. Particularly privileged to be talking to folks who are not astronomers. We astrophysicists are usually sort of guilty of a perspective which is often considered somewhat abnormal. And without any hesitation, I'll absolutely get into that perspective and give it to you. This is a picture I really love. This is taken by Dorje Amchuk, who is not an astronomer, but he's a staff scientist at the Indian Astronomical Observatories in Hanle, Ladakh. The image was taken from the high altitude desert of Hanle, Ladakh. What you see here is the Milky Way, that dark arch-like structure that you see here is the Milky Way. That's the galaxy that we are part of, the solar system, the sun, the solar system planets are part of. The patch of sky that you're looking at hosts millions and millions of stars. But the only star that we know hosts a planet, which hosts life, is the sun. And this picture was taken from that planet, Earth. So it's important to understand how life came to be in this universe. What is the importance of a star in terms of its activity and how it influences our space environment, and what this means for the search of life in other planets beyond our own solar system, which are typically known as exoplanets. So I study the solar system. I'm particularly interested in the activity of the star, not just from a very fundamental perspective, but also from the perspective of understanding how it influences our planetary environment, as well as human technologies that are up in space. And I try to understand it from both observations as well as modeling. And I'll try to give you a sense of that perspective today. Let me also give you the caveat that, when I was talking about this at lunch, I was told by one of your faculty that, since ages, some people have looked at the universe and gone completely mad. This is what we do. And I'm going to talk about some people as we go along who have looked at the universe since ages. I do not know whether they've gone completely mad or not. But here is the solar system. And this is a perspective that the Voyager mission, which is the furthest that any human-made object has ever been, would see if it had eyes. What you see here is the sun in the center. You see this plasma bubble. It's really a plasma bubble. That's known as the heliosphere. That's where the plasma winds from the sun encompasses the space, and the solar system is moving through the interstellar medium, and you see a bow shock there. Within this domain, the heliosphere, the most dynamic object is the sun, and the sun modulates or governs the environment of all planets that is located within the heliosphere. Now, when we talk about an environment in space, that is somewhat unusual in the sense that we have often been talked into thinking that the atmosphere ends where it ends, and beyond that, there is nothing. That's mostly true. But in fact, the space is not always completely empty. The space is full of photons, and these photons can range in energies up to very, very high energies, which can have important consequences. They're energetic particles in space. And as we'll show you, there are other events, transient events in space, which are quite interesting, which does the interesting things to our space environment. The Earth is somewhere out there. Now, if I zoom in into the Sun-Earth system, then this is what you see. This is not a simulation. It is actually observations, and these observations have been put together by observations at the Ooty radio astronomical observatories by our very senior colleague P.K. Manoharan through a technique known as interplanetary scintillations. What you see are density perturbations in the domain of space between the sun and the Earth. And these perturbations that you see are transient traveling perturbations that are originating in the sun. And these are primarily constituting of plasma winds from the sun and large-scale magnetic storms, which are known as solar coronal mass ejections. This variable environment in space is modulated by the activity of the sun. And there is no other image than this image, which gives you a sense of how dynamic the space environment could in principle be. Yes. This is about a few weeks of observations that have been stretched together to make into a movie. This is actually not a wavelength. So what this is you look at stars in the background in radio, and then look at how it's flickering in the radio wavelength. And then from that flicker, you reconstruct the perturbation in density in the intervening medium that results in this flickering in radio. So it's called interplanetary scintillation technique. And so it's kind of the density perturbations are reconstructed through this technique. Let's go back a little bit to the genesis of scientific revolution in the early 1600s to Galileo Galilei. So after the telescope was invented, many astronomers almost simultaneously trained the telescope at various astronomical objects, including the sun. The pioneers of observing the sun in this time were Galileo Galilei, Christoph Scheiner, who was employed by the church, but Galileo was not employed by the church. And Johannes Fabricius was an English astronomer. So what you see here is actually a drawing by Galileo Galilei of sunspots. So these sunspots have been observed since the early 1600s. There are two interesting things that, one interesting thing that I want to convey to you, and one interesting thing that I learned today at lunch. And yes, I confirmed this today at lunch, and yesterday I learned it for the first time. I didn't believe him when he said that. So Manoj claimed that the TIFR colloquium series is the longest running continuous colloquium series in the country. I got this confirmed today at lunch by various people that it is indeed the longest running continuous colloquium series in the country. So it's actually quite a privilege to be talking here. It's the second time I'm talking here. The sunspot observations, by the way, and I'm sure 90% of you don't know that, constitutes the longest running time series of any naturally occurring phenomena in the universe. I'll repeat that. The sunspot observations constitute longest running time series of any naturally observed phenomena in the universe, period. Okay. And here is the observations. In fact, we have these observations in 1611 all the way to the current time, starting with Galileo Galilei and his contemporaries. What you know now that there is a cycle of sunspots, and interestingly, we also know some more aspects of our sunspots we didn't know in the first 300, 400 years of sunspot observations. And that's primarily that sunspots are magnetic. So this was discovered in 1909 by George Ellery Hale, who used an instrument called magnetograph to figure out that there are very strong magnetic fields within sunspots on the order of few thousand Gauss, as compared to the other parts of the sun, which is relatively quieter in terms of magnetic activity on the order of few Gauss, maybe maximum 100 Gauss or something like this. What you see here is a magnetograph image of the sun. Typically, you see this positive polarities of a sunspot appearing together with a negative polarity, and the positive polarities are denoted by white patches and the negative polarity denoted by black patches. So they're really bipolar sunspot pairs. So what is really going on is essentially magnetic loops, which is coming out of the sun and then going back. So when it's coming out, it's a positive radial field, and those are these white patches. Where it's going back down, it's a negative radial field, so it's a black patch. So without going into technical details, we see a lot of spots, which are known as sunspots on the sun. And this kind of spots have also been observed in other stars, and they're known as star spots. Now, these regions are also called active regions. The reason they're called active regions is because most of the sun's activity is tied to these strongly magnetized spots. For example, the image that I'm going to show you next is from the National Solar Dynamics Observatory, extreme ultraviolet image. You see this very bright regions on the sun. This image is taken co-temporally, co-spatially from the same satellite as the magnetograph observation. And you see that the sun's outer atmosphere, which is known as the corona, is extremely bright in extreme ultraviolet over the regions where the strongly magnetized sunspots are present. That's pretty obvious from this co-temporal, co-spatial image. Okay. And obviously, this tells you that then the sun's magnetic fields have something to do with this intense high energy radiation that is coming out from the star. And that is indeed true. If you now follow the energy output from the sun and measure it with satellites just outside of Earth, you get a physical parameter that's called the total solar radiance. That's the energy input from the sun per unit area per unit time into the Earth system. That's the primary driver, natural driver of the Earth's atmospheric dynamics and climate system, and of course of every other planet that is there in the solar system. What we then find is we have this observations for the last 30 years from satellites that radiation is actually modulated, and that modulation is strongly coupled to the magnetic output of the sun. For example, here on the bottom is the sunspot time series. On the top is the total solar radiance. And you find that when the sun is more strongly active with more sunspots appearing on the sun, the energy output from the sun also increases. And this is significant because then you have a connection between the magnetism of a star and its energy output across decadal to millennium timescales. And this energy output of the radiation actually impacts planetary atmospheres and climates. Not only that, it impacts our space environment and determines satellite lifetimes, mission planning, and mission launch dates, etc., etc. Okay. Yes. Yes.
It probably depend on your definition of what a sunspot is, how wide it is. Do you consider two that are nearby to be one or not merged, etc., and that also depends on instrument resolution. So
that's right. So that's exactly right. So what happens is there is a standard definition of what an active region is. So what is plotted is the active region, and that is followed by a international convention by the NOAA administration. So every active region is given a NOAA number, and there is a sort of an international consortium which looks at that every couple of decades and then comes up with a new convention on how to define it. But typically, you don't, you have a threshold in the magnetic field, and below that threshold, you consider the quiet sun region, not the active region. The instrument resolution is a more serious question in the sense that when you put together a time series, that time series is not from any one instrument; it's through multiple different instruments, and so that is something. Inter-instrument calibration is a very technical and more involved task, which is taken over by the people who maintain the international sunspot record.
Yeah, so I just wanted to clarify this convention by which this is defined. That is kind of made up independent
standard.
Yeah, but that is made up independent of assuming this correlation exists.
Yeah, absolutely. Yes, absolutely. Yes. They're completely independent of each other. Okay. So now, when you zoom into a spot, sometimes you find that there is very highly energetic events known as flares. These are storms, magnetic storms. There are two kinds. One is flares. Flares are more confined to sunspots or active regions. Here you see a storm from the Japanese satellite Hinode, where you see a sudden destabilization in the sunspot structure, and it seems to erupt in very high energy radiation. And this is actually, even though you don't see it, there are also highly energetic particles which are known as solar energetic particles, which travel at roughly about 1/10 the speed of light. And they can be pretty damaging to satellite electronics, for example, and sensors which are in orbit, even to avionic systems in aircrafts. So this typically a large sunspot can, just to give you a scale, can fit in something like 50 Earths. So think of it of that scale. Visible surface. Yes, so you're seeing a visible surface, of course, and this is a pretty large spot. So this is roughly, my guess would be this is roughly 50 Earths. So Earth's diameter is, roughly 6,000, well, roughly 12,800. So now you can figure out the scale. So it can be, and last year there was a spot which was 104 times the size of the Earth. So it can be pretty big sometimes. It can be fairly large. So we're talking about very large scales here. But there are even larger scales. And the larger scales is the sun's outer atmosphere, which is the corona. What you're again looking here is a satellite observation of the outer solar atmosphere. Now, this is, we can look at it, I mean, it's a pretty picture, but there is beautiful physics also. You are really literally seeing magnetic fields, and you don't see magnetic fields, right? We do not see magnetic fields. You are seeing magnetic fields here. So two different physics which comes into play here. One is flux freezing. In high magnetic resonance number system, magnetic field, I'll explain it to you, basically is frozen to plasma. And the second is magnetic reconnection and energy release, which lights up the plasma. Magnetic energy is converted to other forms of energy. So it's a non-thermal heating. So first of all, because the magnetic fields are frozen in the plasma, they're stuck to the plasma. And then wherever the magnetic field is stuck to the plasma through magnetic reconnection and waves, it's releasing energy that plasma is lighting up. So literally through this chance of two different physics coming together, you can see, not only see magnetic fields, you can see magnetic loops in action as they're moving around. Okay. And this I find to be quite beautiful. The point is that magnetic fields are a conduit of energy. Sometimes magnetic fields can violently destroy each other in a process known as magnetic reconnection and release energy. And often other phenomena such as waves, where you get hold of the foot points of the magnetic field on the sun's surface and move them around through turbulent buffeting, will create waves which will go and get dissipated in the outer atmosphere, again dumping energy. And then there are plasma jets, which are driven again by magnetic reconnection, which is like fountains of plasma which can be driven up from the sun's surface out into the corona and heat up the corona. And from there, all of this also result in other important dynamics such as coronal mass ejections and the birth of the solar wind, which I'll also briefly talk about. Okay, so what you see here is a large-scale magnetic storm, the largest scales that is possible in terms of magnetic storms, which are known as coronal mass ejections. This is literally a filament eruption. A filament is a large-scale magnetic structure, much bigger than a sunspot. It can roughly occupy something like half the visible solar hemisphere sometimes. So you can imagine the scale of these events. This is again captured through a satellite. The Earth has been put there for scale. The Earth is obviously not there. It's not that close to the sun, thankfully. These storms can be sometimes, not always, sometimes directed towards Earth. When they are directed towards Earth, they create a phenomena which is known as geomagnetic storms. On the left is a simulation of a geomagnetic storm from the NOAA Space Weather Prediction Center. Typically, they tend to be confined near the polar regions. So this one, for example, the pole is right there and it's confined to the polar regions. When the geomagnetic storm is very intense, they can propagate down to lower latitudes. For example, last year in over 10 to 12 May, a geomagnetic storm produced red auroras even in Ladakh. Okay. You see a geomagnetic storm from space here, from the International Space Station. And of course, a beautiful manifestation of geomagnetic storms is auroras, which you see here from Earth. And I've been fortunate enough to see this once from a place north of Oulu in Finland near the Arctic Circle. This is not a picture I took. I just grabbed it from the internet to show you that there's this beautiful phenomena, which is also created by the solar wind and coronal mass ejections impacting the Earth's magnetosphere and upper atmosphere. If anybody is interested in learning about the details of how this is triggered, feel free to talk to me later on. I'm here until tomorrow afternoon. I don't want to get into too much technicalities in this particular talk. So what are the impacts of this? So some of the impacts range from satellite operations at higher orbits to lower orbits, to all the technologies that are dependent on satellites. For example, telecommunications, navigational networks, which all of us use, offshore drilling, which is dependent on precise positioning knowledge of where you are drilling, electric power grid failures. In Quebec, 1989, a big solar flare resulted in a geomagnetic storm which took down the North American power grid for a couple of days, and cities like Montreal was without power over the winter time, which is quite quite catastrophic for them. It also impacts air traffic over polar routes because the polar regions are more susceptible to impacts of space weather and geomagnetic storms. And so the number of flights over the polar routes has increased since the time the space weather predictions have become available. And then 2022, a very unusual event happened. We know that satellites are impacted by these storms, but then a whole suite of satellites, 40 Starlink satellites at one go were killed by a geomagnetic storm. And that's a fairly interesting event that we'll come back to at the end of my talk. So this is just an overview of all the sectors, the societal sectors that are impacted by this influence of solar activity on our planetary environment. And if you look at all the things that I've written down at the bottom, except the last two, which is electric power grids and oil pipelines, everything else actually also impacts Indians and every bit of the functioning of Indian society. So we cannot claim that just because we are not anywhere near the North Pole, we are not subject to space weather. We very much are, because we are a space-reliant society, and we are slowly waking up to that fact. All right. So how do we sort of make sense of all of this? So one way to make sense of all of this is through observations. You have telescopes. You build these telescopes, instruments. This can range from observing instruments, is looking at the electromagnetic spectrum, to particle detectors, which is looking at solar energetic particles, to magnetic sensors called magnetometers, which is looking at the in situ magnetic field, and magnetographs, which is using the Zeeman splitting of lines to image magnetic fields which is far away, like for example in a faraway star, right? Whole set of instruments can be put together. Some of the instruments can be on the ground, but most of the instruments which are looking at the spectrum of light that doesn't make it through the atmosphere has to be in space. And of course, to look at the local space environment, you have to be in space. So most of the observing instruments that we rely upon for looking at the Sun-Earth system is actually up on space. We have about 3 dozen satellites, which tells you the importance that spacefaring nations give to this field in terms of observing the variable space environment, the sun's activity. And India has its first eyes on the sun, the Aditya L1 mission, which was launched in 2023. It also has a host of instruments that's looking at solar activity as well as the in situ space environment. Okay. We also look at the sun through the eyes of our mind, which is what a theoretical physicist does. And that is primarily where I sort of come in. I also do a lot of data analysis, but this is my primary forte. So you try to understand the physics of how how a star works, and then try to model it, and then push these models to data-driven predictions, which can be utilized to understand the space around us and the impact of solar activity and the technologies that we have. So the sun is a typical G-type star. So if you look at the entry of such a star, then we know that light at its core, which is within the inner 40% of the sun, the energy is created by fusing helium to hydrogen. And that energy is first radiated through the inner 70% of the sun through multiple sort of emission and reabsorption of the photons. That's that inner 70% called the radiation zone. And then the photons hit a layer when it's about 70% out of the sun, where the plasma becomes opaque to radiation, and the energy is dumped there, and it hits up the plasma, it expands, becomes lighter, and then upwells to the surface. Comes to the surface, radiates its energy, and then becomes denser, cooler, sinks back down. So the outer 30% is where there is vigorous convection. And of course, the temperature inside the sun is extremely high, ranging from about 12 million degrees in the center to close to about 5,600 degrees Kelvin near the surface. So the matter is completely ionized. So you're dealing with a system where you don't have atoms in its entirety as a neutral atom, but it's been broken up into ions and electrons. So essentially, you're dealing with a plasma system. And because the convection zone is highly dynamic, the plasma is moving around, you're dealing with dynamics. And the field, the physics that you need to use to understand this sort of subjects is known as magnetohydrodynamics, which is kind of one step above fluid dynamics, where now you're not dealing with neutral fluids, but dealing with the dynamics of magnetized plasma systems. Okay. All right. I promise I'll not be dealing too much in equations, but there's something fundamental. What you see on top tells you it's the magnetic induction equation. How does a magnetic field evolve in a plasma system given some certain plasma flow velocities and diffusivity? You can imagine that if you get rid of the first term, it is basically a diffusion equation. So essentially, magnetic fields will diffuse away, which means for a system to sustain magnetic fields, the first term is very important, the curl of V Crosby term, and V is essentially the plasma velocity sitting there, right? So very naively, without getting into any details, I can just tell you this much. So therefore, to create and sustain magnetic fields in a system, you need to have plasma motions. You need to have velocities, speeds, which feeds some sort of energy into a mechanism that creates magnetic fields. We call that the magnetohydrodynamic dynamo mechanism. I have one slide on that. But the other thing that is very important is in astrophysical systems, the length scales and the velocity scales are very large. Now, if you take the ratio of the first term to the second term, you have a dimensionless number, which is known as the magnetic Reynolds number. Just like the Reynolds number in fluid dynamics, you have the equivalent of that in MHD. And that's the product of velocity and length scales to the diffusivity of the system. Because in astrophysical systems, these scales are very high, the magnetic Reynolds number is also very high. Now, if that is the case, then you can essentially show that the diffusion timescales are very, very large. Since diffusion is very inefficient compared to the flow timescales. Okay, when magnetic Reynolds number is large. Literally means that the magnetic fields will remain frozen in the plasma flow and will behave as the plasma dictates them to behave, and not diffuse much when our magnetic Reynolds number is very high. This implies if I have shearing flows or whatever in that medium, the magnetic fields get sheared, and if I did not have originally a Bx component of the magnetic field, but started only with a vertical component, I can produce another component which is a Bx or horizontal component of the magnetic field. That is only possible because the energy in the plasma flows is being fed in into this system, and magnetic Reynolds number is high. The plasma beta, which is the ratio of the gas pressure to the magnetic pressure, is also high. So the plasma dominates the magnetic fields in the sun's convection zone. This is a zone inside of a star like the sun that magnetic dynamo action is possible and magnetic fields can be created. So there is another bit of physics I want to talk about, which is also quite interesting. When magnetic fields and you bring them close together, you might have a situation where magnetic fields that are pointed in different directions come together. Now, that is a situation that is not allowed. And for condensed matter physicists, the equivalent is a topological defect, okay? Or in other sense, it can be a discontinuity, right? So this is entirely possible in a system where there is plasma motions and magnetic fields are frozen in a plasma, because often the plasma motion can bring together magnetic fields which are oppositely directed. Because it is not allowed for any point in space to have magnetic fields which are pointed in different directions, the magnetic fields will violently reconnect and produce different sets of field lines from the original field line. And in the process, some of the magnetic flux is lost. Okay. Now, magnetic fields have energy, and you all know that. So what happens to the magnetic energy? So through the process of magnetic reconnection, the lost magnetic field is converted to thermal energy. It also creates energy which accelerates particles in this region where the antiparallel magnetic fields are coming in touch. These are known as current sheets. These are regions of intense currents, which is J essentially in the lingo of electrodynamics. In these regions, you'll have a lot of heating, you'll have a lot of particle acceleration. Flares and coronal mass ejections are essentially born from this magnetic reconnection events. Okay, and this is what powers all this energy that's there in these magnetic storms. Okay, with that, I'll go into a little bit of glimpses of the research that we have done. For example, looking at the interior of a star like the sun, to look at how magnetic fields are produced. Now, as you would notice here, this is the convection zone of the sun. And what is plotted is two different components of the magnetic field. One of them is the toroidal component, which is in the phi direction. The other is the poloidal component, which creates the global dipolar field. in the earth theta plane. It's this toroidal component which is much stronger than the poloidal component that's produced by the differential rotation of the sun. And when they are very strong, they become buoyant and they rise up through the interior and pierce the surface, creating two spots where in one of the spots the magnetic field is coming out, in the other spot the magnetic field is going down, and that's essentially a pair of sunspots that is produced. This is how the magnetic dynamo in the interior of a star produces the spots that you see on the surface of the sun. Now, you can actually stretch these models now. Over the last 10 years, we have developed that capability where you can write these models through an observation of a certain component of the field and flows to turn this not just as a means to understand what's going on in the sun to what is known as a predictive model. So what you see here is a prediction for the current solar cycle, cycle 25, which started in 2019. This prediction was, well, we finished this work in 2017, but eventually the paper came out in 2018. The black curve in the background is the actual sunspot observations. The red curve is our predictions, reconstruction and predictions. What you see here is the first century scale reconstruction of solar activity by any physics-based model. What you see here is the first dynamo-based prediction of cycle 25 as well. And the surprising thing was that at the time when he made the prediction, the community felt through various curve fitting exercises, which I don't consider very scientific, that cycle 25 is going to be either very weak or non-existent. The sun is going to slide into a minimum kind of phase. The reason of that was that over the last 3-4 decades, the sun's activity was continuously sliding, as you see. So ours is the first prediction to point out that sunspot cycle 25 is not only going to happen, it is going to buckle the trend and is going to be stronger than the previous sunspot cycle 24. Our prediction contradicted the NASA NOAA prediction, panel prediction, who predicted a weak cycle in 2018. But now,
so what was different in your model which made you?
So I'll come to that. So now what we have is the cycle that is already in progress, and we think it's somewhat dangerous to make that statement. We think we are past the peak, but clearly the peak is already stronger than the previous peak. That much is for sure. We think the peak happened in 2024, December, which was also one of our predictions is going to happen in 2024. But that is a bit of an uncertainty because there could sometimes be a second peak in the cycle. We're not aware of that, whether that's happened or not yet. But certainly the peak was stronger than the previous cycle. So that part of the prediction has been proven correct. The thing that was different, can I just answer his question first because he asked a question? So the thing that was different in our model was that we utilized a technique which is a dual model technique. We simulated the surface magnetic field evolution through one model, which incorporated the actual observations of sunspots coming out, and then for the last 3 years of the cycle, that was synthetic data, which is an ensemble synthetic data input into the model, utilizing a technique or understanding that was called the backpropagation model of the solar dynamo, which we now think is the best model for the solar cycle. Multiple different results, not just ours, multiple different results are now pointing to that fact. So data-driven surface plus transfer model plus dynamo model, 2 different models coupled together, which is, I think, the most sophisticated exercise ever for a solar dynamo-based prediction, using the right kind of physics that was missing in many of the previous models.
So just wondering, so others got all the other maxima, right? But just went wrong with the...
Until our work, most of the other predictions were making only one cycle forecast, only the future cycle forecast. They were not making multiple cycle reconstructions. We screwed up with cycle 19, as you can see, but now this week we have a paper in Astronomy Letters where we have managed to reconstruct this. This was quite a problem for the whole community, but anyway, so that's another story I'll not tell today. Yeah.
There are timescales in the problem. What is the rising timescale and the falling timescale? And the timescale at which they repeat the pattern. So what controls this timescale?
Okay, so the rising timescale is controlled by what is called the induction mechanism. That's the rate at which the poloidal component of the field is being converted by differential rotation to the toroidal component, which is producing the sunspot cycle. The following component of the field is essentially governed by the decay time scale. So once you have produced a a kind of a reservoir of the toroidal component of the field, which is residing in the convection zone, how fast is it decaying? And that's governed by the diffusion time scale at the base of the convection zone.
It seems pretty consistent
Yes,
across these decades observation. So
right.
why is that so critical?
Because the physics is universal here. The physics doesn't change from one cycle to other. The physics is the same. The seed of the cycle at what you are using as input to the cycle before the cycle starts is changing. And that's the polarized component of the magnetic field which acts as seeds of all of this cycle. And that is what is produced near the surface layers by the decay of sunspots. And that's something that we simulate with a surface flux transport model. That is the kind of model that we coupled with the dynamo model to get this simulation.
I think Sushil, I just needed a quick clarification
Yeah.
on the last thing,
Mhm.
which is the main.
This one, right? Yeah.
That means-
Yeah, so basically, you see, we used for the last bit of cycle 24, because we make the prediction before the end of cycle 24, we had synthetic inputs and we made an ensemble of inputs. I think, if I remember correctly, I think we had something like 140 different ensemble runs, which means that you now have a range of predictions. So the two different, the top and the bottom black curve are the upper range and the lower range of our prediction. The red one was the most likely run.
Is that? That's what deleted.
Until here. After that, everything is prediction after that. After that, everything is prediction. Yeah. So this, the black observations.
It's been a very short time.
So until here is the observation. Beyond that is no observation. This is all prediction. After 23.
Say that we are already.
Oh, so you can just open your phone, just look at international transport number, and it'll go to a site called well, it's the international transport number time series is officially maintained by the Royal Observatory of Belgium. The official by degree of UN there, they keep the transport number. You can just see it there. You can easily see it. So you can, in fact, you can see the following. Maybe after my talk, I'll just quickly Google and show you the current cycle. So yeah.
Yeah, you mentioned that the small disagreement in cycle 19 was
It's not
the one.
small. It's quite a
Yeah.
big disagreement.
Yeah, but I would evaluate a disagreement based on also uncertainties around the central value, and
Right.
your simulation has some unknown uncertainty which is clearly
Yeah.
not plotted, and your data, if you look at the scatter around it as uncertainty, I would say that is within 1 sigma, and
Yeah.
I would think the problematic ones are towards the end of the cycle 23 and cycle 22, because there you have much stronger disagreements.
So in fact, if you look at the whole series, one systematic problem you will notice is that what you're pointing out is the mismatch between the minimum of the cycle. We never get the floor right. We get the peak right, the minimum we never get right. So, and we are not predicting the minimum floor anyway, but we never get the minimum to be as low as it typically is. And we know why it's the problem, but yeah, we didn't try to solve it because that was not the main aim. Anyway. Yeah, any more questions related to this? Okay. All right. So now from the sunspot cycle and move closer to Earth. Okay, and there is also some beautiful physics which is not so difficult to understand here. Okay. All right, there is a sun there, and then the sun is spewing out this supersonic plasma wind. Now, if you have ever walked, through a very strong wind, I presume you have over the last 3 days, there's been quite a stormy weather here. You feel a resistance, right? It's because the wind is dumping momentum on you, right? There's something called dynamic pressure. So if you are facing an onslaught of supersonic plasma wind, you are being forced by this dynamic pressure of this wind. All stars have this wind, and this is going to be a recurrent story for the rest of my talk, where I'll keep coming back to it. That wind, plasma wind, that is originating in the sun, is also taking the magnetic field from the sun into interplanetary space. Every planet is sitting in this environment of plasma wind. Now the Earth has its own magnetosphere. Okay. Now, when you have magnetic fields, magnetic field also have a pressure, which is basically v squared by 8 pi, right? So now let us hypothetically imagine what does it take to stop the wind of a star and not let it enter. And so in Bombay, you've been facing the natural wind of the atmosphere. Have you been facing any plasma wind? I presume not, right? Something has happened. Some physics has played out somewhere, right? Okay, let's talk about the physics a little bit here. All right, so let's assume that there is a boundary like this, and I need to stop the solar wind there. What this implies is on the left-hand side of that boundary, the sun side of that boundary, the dynamic pressure of the wind, the thermal pressure of the wind, and the magnetic pressure, because the wind is also carrying the solar magnetic field with it, has to be equal to the thermal pressure and the magnetic pressure of the Earth's magnetosphere. Okay, because the Earth's atmosphere is not expanding, there is no dynamic pressure from our side, from this side, right? So if such a balance is achieved, then I can literally stop the solar wind there, right? That is exactly what happens. Okay, there is this boundary which is known as the magnetopause. Magnetopause is where the magnetic fields of the Earth get squeezed by the onslaught of the solar wind. Because it's getting squeezed, the magnetic pressure increases, keeps on increasing. At some point in time, the magnetic pressure and thermal pressure on the Earth side equals all the stuff that's being thrown at you from the sun, which is the dynamic pressure, thermal pressure, and magnetic pressure in the solar wind, and stops it. Okay, we can simulate this, of course. Okay, so this is a different set of models completely now. These are called star-planet interaction model. This is the first such model that was developed in India by our group. And this is also a slide that tells you why do we live? Why is there habitability on a planet like Earth from the astrophysical perspective? So what you see here is a model of the solar plasma wind impinging on the Earth's magnetosphere. And then what you see here is the magnetic fields of the Earth's magnetosphere getting squeezed and the magnetopause forming out here. Magnetopause is the region where the solar wind literally stops and cannot enter or come closer to the Earth. Okay. These are the deformed magnetic field lines of planet Earth. These are the pristine magnetic fields that is in the solar wind. The Earth's atmosphere now, remember, is only 60 kilometers in height. 60 kilometers. That's how fragile our existence is. But the magnetopause boundary, thankfully, is variable. It's a dynamic boundary, but it's between 5 to 8 times the radius of the Earth. Okay, far beyond the atmosphere. So our Earth's atmosphere is well protected, okay, by the magnetosphere. If the magnetosphere was not there, then our atmosphere would have been exposed to the solar wind. So what happens if your atmosphere gets exposed to the solar wind? Well, so first let's consider what happens if you increase the speed of the solar wind. The more you increase the speed of the solar wind, the magnetopause boundary keeps coming closer and closer to the Earth. And that's obvious because the dynamic pressure, which is proportional to half rho v square, increases. And so you can imagine with a very strong wind, you might enter the terrain where you are eating up the atmosphere. The solar wind comes into direct contact with the atmosphere, right? Yes. Yeah.
To the rotation of the Earth, whether there's some diurnal effect over here.
Every day. So that's basically right. So essentially this one, here you see this configuration, every 24 hours, the other part of the Earth will be facing this. And so essentially this boundary dynamically changes as the Earth revolves, and different parts of the Earth which faces the sun has to come up with that boundary, has to come to equilibrate with that boundary. So in fact, the tilt of the axial magnetic dipole, which is also dependent on how the tilt of the magnetic dipole is related to the Earth's rotation axis, and the seasonality also determines this equilibrium. So it changes from season to season also. And that's another story which we are exploring now. How does seasonality impact this balance? Okay. So the Mars is a beautiful story. It's a beautiful story because Mars had a magnetosphere. It had a magnetosphere until about 1.5 billion years into its age. And it is thought that in the early Mars had an atmosphere, sustained greenhouse gases, and could have been conducive to life. And therefore, all these missions to go and explore whether there is some semblance of life or some evidence of at least past life on Mars. But if you look at Mars today, it doesn't have a global magnetosphere. and neither does it have a global atmosphere. It has a very thin carbon dioxide rich atmosphere. It is just 50 meters in thickness, 50 meters, that's it. It's basically atmosphereless. So what happened to planet Mars? So we wanted to simulate that. So this is a simulation of solar wind interaction with planet Mars, and what you see here is this magnetic fields of the solar wind draping around planet Mars, but then slipping past it and moving back into the downstream side. And the net impact of that is that the solar wind magnetic field and the plasma gets coupled to the Martian atmosphere viscously and carries away the Martian atmosphere with it. And this is more abundant in the picture here, where the background density is plotted in the simulations. And you see a massive loss of atmospheric density of an assumed Mars with an atmosphere on which a solar wind is imposed. You can see this almost like a cometary tail. You see how the mass loss is happening because of the lack of a magnetosphere. So magnetosphere is something that is very crucial for the existence of planetary atmosphere, the ability of a planet to hold on to an atmosphere. Okay, how much time do you have? Assuming that I started late and with all these questions. Yeah, good. Yeah, I'm going to negotiate. Yes. Yeah. It is really a surface. It's not a line. Yeah.
That really depends on how much magnetic field you have for the Earth as well, right? So what kind of fluxes you would need to create certain distances?
Yeah,
Do you
so
have
I
numbers?
will have a proper parameter space study thrown up, not so far from now. Just give me a few moments. It'll come. We have done that parameter space study. Okay, so now we want to step beyond the solar system. I'll be guided by two philosophy. One is we want to study the Sun Earth system because it's an important system. It's the only system we have evidence of life, right? So it's important to understand the Sun Earth system before you go beyond and claim that you understand or your models are working in other systems. We want to prove ourselves with the Sun Earth system first. Second is, well, absence of evidence is not evidence of absence. We may not have found any evidence of life on other planets, which doesn't mean exoplanets, which doesn't mean that there is no life or that we should not be looking for it. At least we can be figuring out what planet has the possibility or the right kind of environment to host life. As the next set of work is being motivated by this purely esoteric, no application sort of motivation. Okay. All right. If you look at and there are many people here, you have a very nice exoplanet group here. If you look at the number of exoplanets that has been discovered until now, it's upwards, I think, close to 6,000 now, 5,963 or something as of yesterday. I was checking the internet. Exoplanets that have been discovered, out of which about 4% is Earth-like rocky extraterrestrial planets, which means, well, roughly on the order of, I think, 240 or something like this, right? But the curious thing is, because they're so far off beyond the solar system, we have zero idea about their magnetism. We have some ideas about the magnetism of their host stars, but zero idea about the magnetism because we have no observational constraints. They can be anything. And when you have such a thing, it's the dream of a physicist like me, right? I mean, it's a theoretical physicist's dream. You have no constraints. You can play, right? And you can try to understand, set forth the hypothesis on how things are going to be in this zoo of exoplanets. So that's what I'm going to look at. And the reason I'm going to look at this is because we know, at least for the Sun Earth system, that the star's activity is the primary enforcer through its solar wind or stellar wind, through its radiation, through its energetic particle deposition, the primary influencer of the space environment and atmospheric mass loss in planetary environments. So it's a problem worth looking at in the context of exoplanets as well. Now, if you look at the range of activity that is only possible even only for the sun in sun-like stars, you know that the activity slowly decreases with age. In fact, if you look at the sun at its present age, about 4.6 billion years, it's somewhere way down in the activity level. This is based on X-rays of coronal X-ray luminosity. This is based on more direct measurements of the magnetic field by a technique known as Zeeman Doppler imaging, which is only possible for very rapidly rotating stars. It doesn't work for slow rotators. We know that the magnetic field decreases, the dynamo becomes less efficient as the stars age. Okay. So obviously the magnetic field of a sun-like star itself has changed over its evolution, and the different stars are born with different masses, different sizes, and so they have their dynamos are efficient to different levels, so they have different magnetic fields. You can imagine that a star has a whole zoo of magnetic fields possible. Just like a planet in principle can also have different levels of magnetic field possible. Like if you look at Jupiter, which is much more strongly magnetized than Earth. Okay. There is this curious stuff that was going on in the last 10 years in the field, that it looked like the sun is less active than other sun-like stars. Couple of very high-profile papers pointed this out. And the question was, why is this the case? So I want to take a stop briefly and explain this a little bit here, because this is like a midlife crisis of the sun. A sun-like star is exactly at its midlife. It's like a midlife crisis. Without going into technical details, we published a letter in MNRAS a few years back where he explained why this is happening. I want to put this here because this is a technical paper, but I have a little cartoon to explain this because nonlinear dynamics people in this room might be interested in this work. So what goes on is this. This is age, this is increasing age. As a star ages, it loses angular momentum because the wind is taking away angular momentum and the dynamo becomes less efficient. As the dynamo becomes less efficient, essentially the energy that's stirring the pot, that's feeding in or forcing the system is falling. And eventually it reaches a point where there's a bifurcation. And suddenly two modes of activity, one is an active mode and another is a low activity mode, which becomes available to the magnetic dynamo mechanism. And when that happens, then the possibility opens up for a star-like star to be much less active than other solar-like stars. And this results in not just in its radiation, but also its rotation activity relationship breaking down. It's called a stellar chronology relationship. And we could explain all these observations that has happened in the last few years with this kind of a hypothesis. So now we come to the interplay of stellar planetary magnetism and look at what happens if the star is much more magnetically active than the present sun. So what you see here is a simulation where you literally see that the magnetosphere of the planet getting ripped apart and forming this beautiful structure which is known as Alfvén wings, following Hannes Alfvén, who made some fundamental contributions to MHD. What this does, it opens up the possibility of much greater mass loss from even a magnetized planet. Okay. So we wanted to explore what happens if we put all of this together in a zoo of simulations, like tens of simulations with different stellar magnetic fields and planetary magnetic field strengths. What you see are results of different simulations with different magnetic fields for the star and the planet. And I don't want you to interpret it. What I can tell you is this: for a planet with the same magnetic field, if we increase the stellar magnetic field in its wind, then mass loss increases. Okay. Now, very curiously, we also found that if the stellar wind magnetic field and the planetary magnetic field is the same, but both are increased, so the ratio is still constant, but both are increased, even then there are higher mass loss. And that is because of the formation of higher current sheet regions, which enhances mass loss by opening up the atmosphere to the solar or stellar winds. Now, this is a bunch of simulation. You can actually also work out the analytics to a certain point where you get stuck, and then you have to get something out of the simulation, which is where does the magnetopause form, the magnetopause stand-up distance. Once you get that and you put it in an analytic formulation, you can create a relationship which can predict this. Given any planet and any star, what would my mass loss rate look like? And we did that. And it exactly matched these simulations, except that one point which we have to get out of the simulation, which is the magnetosphere stand-up distance. The reason it cannot come out analytically is because it depends on magnetic reconnection. Okay, magnetic reconnection dictates where the magnetosphere stand-up distance is, and that's something that you have to get out of simulations. So this, we think, is an important tool now to predict mass loss rates in any star-planet system that you give me.
What is BE here?
B is which B are you talking about?
BP is equal to 0.5 BE.
Is mass of the planet, the planetary magnetic.
So what is
field.
BE?
B is where? Hold on.
BP is equal to 0.5 BE, BP is equal to
Oh,
BE.
so those B is Earth's magnetic field.
Oh, it's-
Yeah. Mass of the planet doesn't play a role here because the mass of the planet is essentially the size of the mass of the size will eventually interact based on the size of the atmosphere that you have. The mass of the planet, the only role that it plays is through gravitational interaction. So that's what you can say. But otherwise, it's MHD blind. But the gravity is in the system. So if you have higher density planet, then it will tend to hold the atmosphere better compared to a higher density planet. So that's where the mass comes into play in the system. Yes, if we have assumed out like planet. That's right. Yeah.
These
Yes.
simulations, you just mentioned gravity is somehow involved in, but how relativistic are these stuff?
These are not relativistic at all. None of the calculations I've shown you is relativistic. Completely non-relativistic calculations. Okay. Which rotation? So if you change, so in this, rotation is not even coming into consideration. You're essentially considering a fixed Earth-like planet. Rotation doesn't play a role here because within 24 hours, you're essentially too fast, right? And the simulations are lasting over much longer time scales. So you don't worry about a rotational time scale here. For all practical purposes, over long time scales, the rotation is unimportant because it's just too fast. So every side of the planet is seeing the wind, so to speak.
Reorient the magnetic field.
Oh, then it will be
That's
completely
the
different.
difference, right?
Absolutely. If, for example, if I do this with Venus, with a highly tilted magnetic dipole, physics will be completely different. You're absolutely right. So the magnetic dipole tilt is very, very important. Okay, the last bit. I told you I'll end with Starlink. In 2022, February, Starlink lost 40 satellites at one go over two days to a space weather event. Starlink put out a press release saying that this was due to unanticipated space weather. And this was widely sort of accepted. This is due to severe space weather. Everybody followed it through. There, in fact, was a prediction of the storm. We also made a prediction of the storm and an alert. It was supposed to be a weak to moderate geomagnetic storm. In fact, it turned out to be a moderate geomagnetic storm. Question was, how did a moderate geomagnetic storm result in such a catastrophe? So we investigated this through simulations. This is a data-driven simulation of the Earth's magnetic field condition during the time. This simulations gives you the current density enhancement in the space environment that is directly correlated to the expansion of the Earth's upper atmosphere. So higher the current density, it hits up the upper atmosphere of the Earth and that expands out into low Earth orbit. When it expands out, I'm just explaining the physics qualitatively to you. When it expands to low Earth orbit, the drag faced by satellites in low Earth orbit is increased. It's like walking in air or walking in a swimming pool, which I'm sure many of you have felt, right? So higher density translates to higher drag. The other thing, I'm sure you also are exposed to it, and this is what we figured out step by step. Our first simulation with only space weather, we figured out the geomagnetic storm simply, by itself was not dangerous enough to have taken out all the satellites, the ballistic coefficient of a satellite. Now, ballistic coefficient is something that you can define for anything. It's an engineering concept. If I have an umbrella, and you would have noticed it, if you're trying to walk, let's say in this beautiful little land that you have facing the sea and you have a strong wind, you put the umbrella with this area, orthogonal to the wind, you suddenly get dragged by the umbrella, right? Or if you face it towards the wind, then the umbrella will get a drag, right? Will feel a drag of the wind, right? Now, if you had now imagine a heavy object like a ball, iron ball, and I'm throwing it against the wind, right? By virtue of the fact that it has a high momentum, by virtue of its mass, it will tend to move through this wind in the direction that you endow it with this momentum, right? Ballistic coefficient is the ratio of essentially the mass to its surface area, and it looks at this interplay of essentially the tendency of a body to move in the direction in which its momentum has been imparted versus the drag that it faces because of its area. Okay. Stuff that has higher mass, lower area faces less drag. Okay. We had to get down to the basics of even that for the Starlink satellites. That, along with also the density of the region where it was inserted. They have a very strange way of inserting this. They first insert them at 260 degrees, 260 kilometers, around 200 to 260 kilometers. Then do a bunch of health checks. The satellites which survive the health checks are then boosted up to the nominal orbit, which is about 400 to 500 kilometers. This bunch of satellites were launched into space and deployed at very low Earth orbit, around 200 to 260 kilometers, when the storm was pretty much ongoing and when the density perturbation due to the geomagnetic storm was at its greatest. This is a simulation of geomagnetic storm. I'm not going to go into details of that. Just focus on this plot here. This is the current density enhancement in the magnetosphere from our simulations. This is the atmospheric density enhancement from another model that has been utilized. You see the atmospheric density enhancement happens just a few hours following the current density enhancement because it takes some time for this physics to play out and for the current that's being dumped to hit up the upper atmosphere for to expand up to create the density enhancement. And this is a satellite orbital decay. A Starlink was launched at this dashed, you see this dashed vertical line at this point, all the satellites were launched. It entered orbit when this system was already perturbed. That we found out in combination of a ballistic coefficient, which was somewhat dicey for that low Earth orbit, all came together to result in this catastrophic losses because this was actually highly unusual. I'm proud to say that this is, in fact, I think the most detailed accident investigation in that Starlink event up to date. Okay, it has about 20 citations in 1 year, and I'm pretty proud of this. I led this work with students, even undergrad students. We had some collaborators from NASA and another private agency called PSI in the US. But it opens up the possibility now of actually taking these MHD models, coupling them with atmospheric density perturbation models, and then utilizing this for realistic estimates of satellite orbital decay and predicting the impact of these geomagnetic storms on satellites. So with that, I will end with this. I'll come back to this if you want to have a look at it. I want to acknowledge all the sets of students I have worked with. How many of you are students here? Can you raise your hands? All right, great. Good to see this number. So maybe I'll just 1 minute of remark, I think, here. I mean, I think that is for us, scientists like us, I think students are our life. And I've seen how, things have changed when we were students to how things are now. And I think we are in a very competitive environment right now. And I've been talking about this both within the institute as well as to people in various institutes. I think when I look back, I really didn't know about space weather. I was telling Jairam today that I did not have the term space weather in my thesis when I wrote that thesis about 2 decades back. So I didn't really know what role I'm going to play as the field evolved and how will I even define that evolution of my own field. All that was driving me was the love for the science that I was doing. We didn't bother about citation because that stuff was not available to us. We didn't bother about how many papers some other guy who's sitting next to me is publishing. I think that is fundamentally important as a student for me. That was fundamentally important as a student for me. I think it's fundamentally important for all of us to have the peace of mind that we need to pursue a life in science is the love for what you do. And the rest is noise. Thank you.
Thank you, Dibyendu.
Yeah.
We can have questions.
Thank you very much. I will begin with a historic comment. You may be familiar with Carrington event.
Yeah.
That
1959. Yeah.
1859.
1859.
And that was actually measured in Kolkata.
Yes.
So,
yeah.
So I'm just wondering if an event like that happens, is there any possibility of all this, many of the satellites, they will essentially collapse, or there's a sweet spot for them to survive? Is it possible to investigate that?
Right. So Lloyd's of London was entrusted by the United States and UK Met Office to do an estimate of what is going to happen in terms of economic losses if a Carrington event hits us. They estimated it to be something like on the order of trillions of dollars, not even billions, trillions of dollars, and life coming to any space-dependent life coming to a standstill. Now, if you ask me the question, what is it that we can do we can't geoengineer it's not solar engineer the sun. It's not possible for us to stop such an event from the sun. But it's possible for us to probably make our satellites more resilient to such severe storms. two things that that are required is one is protection from direct impact of high energy photons and energetic particles. The second is, and that can be done by, if you have advanced space weather forecast that such a storm is going to hit, by having shielding mechanisms which can shield satellites, the sun side of the satellites, from extremely energetic photons, gamma rays, X-rays, and solar energetic particles. The second is the ability of satellites to move up in altitude. What is going on is much of the communication and navigational network satellites tend to be at low altitudes, because that's where communication with the ground is more useful, because flux of signal losses are much lower if you are like closer, right? If you have the ability to move boost your altitude from low Earth orbit to higher orbits where you don't face the other part of the storm, which is the geomagnetic storm, which expands the Earth's upper atmosphere. If you can go out of that regime by boosting yourself up and then coming back down when things have stabilized, that's another possibility, which means that you build in these resilient systems into satellites. That's something that is being thought of, but it's not something that is widely done, certainly, at this point in time.
Thank you.
Other questions?
No. Yeah.
So I have a generic question. So just wondering about the parameters that you put in the model. Like how sensitive are the model outcomes to these parameters input, and how do you get these parameters? Like how do you extract, how easy it is to extract from these, these observations? And
so as you can imagine that there are multiple parameters and the models are sensitive to different extents to these different, to different parameters. I mean, the sensitivity levels are not the same. They respond much more to changes in certain parameters than others. Much of the parameters inside the sun come from the field of helioseismology, which is a pretty precise science which tells us about the flows, large-scale flows in the interior of the sun. There's some unknowns which are there. For example, the meridional flow of plasma, which plays a very important role in diurnal mechanism. The interior part of that flow, we don't have a very good handle on, and that's something that is assumed based on theoretical assumptions. So that's there. The viscosity, which also is an important input, comes from standard solar models. We think it's more or less right, but then we don't have any, because you can constrain it on the surface, but we don't really have any constraints on it in the interior, except that plays a role in multiple other things, like again, handling the mixing rates, handling the abundance of light elements on the surface. So from that, you get indirect constraints on the mixing timescales and viscosity and diffusion in the solar interior. So those unknowns are there. So one of the ways that a typical modeler will try to bypass these unknowns is build a model where you calibrate the model to some observation and don't touch the parameters anymore, but only change the input parameter that is observed. These are called data-driven model. The same physics or the same technique is used in climate models, for example. I have a black box. I mean, imagine that I have a black box, right? In which some input is going that is observable, and then output is coming out, right? What I will do is I'll go back in past, first tune the black box with observations. It's not tuning. Observations, put in whatever observations I know, observed constant. The unknown constants I will tune. This is called calibration. To get the output for some past event, I'll match that, right? And then I don't touch the black box. If I touch the black box, then that's unethical. The only thing I touch is the driving, what you're putting in as input, and that input is observable. So it's constrained. And then your output changes. So the predictive runs of these models typically are done in that.
Hey, I just had one question,
Sure.
more curious. Like when you showed the total radiation, how it changes over time, it was around like 0.1% in the total.
Yes, yeah.
So if we include everything else, like the magnetic energy, like I assume that the energy released at the core is much more stable than that over time. So it's a sort of like some sort of like temporary pileup of energy in the outer atmosphere and then sort of oscillatorily releasing. Or if you add up everything, it will turn out to be, constant.
Okay, so essentially, no, the core is fairly stable over longer time scales, right? So that perturbation that you're seeing, that 0.1% perturbation, is really coming from the convection zone. And that's where the magnetic field is playing out the role. So if you want to figure out what is the output from the core, you just average it out, smooth the output over a smoothing window, which is, let's say, 13 months. Then you've got rid of the sunspot cycle completely. And that's your average core output, for example.
That only includes the photons, right? But there's also energy release.
No, so this is total solar radiance across all wavelengths of the electromagnetic spectrum.
And includes the energy lost in the winds, everything.
No, that doesn't include any of this. It doesn't include energy lost in the wind and all that. It doesn't.
But if you include,
but the mass loss rate in the wind is fairly low.
okay,
Over decadal timescales is fairly low. Yeah. I mean, it doesn't make a big dent in solar mass over decadal or even millennium timescale. It's very tenuous flow, right?
Yeah, right. So there is a very popular term called Van Allen belt. Can you just explain?
Yeah,
that
so Van Allen belt, so to go back to the maybe because I think there the simulation might be useful. So okay, so this I can stick here instead of trying to go back too much. Where is it? Okay. So Van Allen belt, so you see this Earth's magnetosphere, right? So now, so this Earth's magnetosphere has this fairly closed field lines, which are fairly stable, the inner part of the closed field lines, not the outer part of the magnetosphere. So when you have some injection of magnetic fields, charge particles into this closed loop magnetic fields, they stay there. They kind of mirror and they go around, keep going around, and then it creates a belt of high energetic particles, which is constantly there. You don't get rid of it, and that's called the Van Allen belt. So every mission that is sent well beyond the Earth's atmosphere, magnetospheric system, we'll have to, to something like, well beyond mu, we'll have to go through the Van Allen radiation belt. And that's a hazardous belt. So often what happens is during launch, it is, all instruments are parked, it's not exposed, and things are unfurled well beyond the Van Allen belt. And that belt also can change based on solar storms because the injected particles can change in there. But that's constantly there, more or less. Even when there is no solar storm, the Van Allen belt is still there.
Dibyendu, I had I'll come to you. I had a question about the relatively low solar activity that you were talking about for Sun. Now, Sun is also a relatively slower rotator compared to other main sequence G-type stars of similar age. Now, there is some statistical evidence to show that stars that host planets are rotating slightly slower than stars without. And the planets are formed in a protoplanetary disk when they were young. And then if the magnetic field thread the protoplanetary disk, it can cause what is known as disk breaking. It can slow down the stellar rotation. So did you consider that aspect of why Sun might be
because we were looking at only in that case, we were only looking at the Sun. And at 4.5 billion years age, right? So that was where? That was somewhere, I think, here, right? So all of these papers dealt with a Sun-like star at an age of 4.5 billion years, by which time there is no protoplanetary disk at all.
No, that is true, but it has already been slowed down.
It has already been slowed down.
So even you look at the current 4.5 million G-type stars, the stars which host planet seem to be rotating.
Yeah, so that's
statistically.
Yeah, that's an interesting connection. I don't know whether it has got to do with this. In the sense that I think it's possible that stars which are slow rotators and has a weaker outflow of winds will have a lower dynamic pressure also. So it will not have. So the planets can come closer in and you can observe them better. So
the activity is very tightly correlated with rotation.
It's possible.
Rotation rate.
Absolutely. That is certainly the case. That is certainly the case.
I'll take a question.
Hi, Dibyendu. Very nice talk. I have a question regarding the last piece where the space satellites got. So how can we save this? Like, what is the typical time scale when the solar activity shows up? And in what time scale it shows up on Earth's atmosphere? So can we inform these companies well in advance, but you can inform them in advance to save them?
Right. Okay. So the various elements, I'll break it down. So solar flares, when a flare happens, couple of things happen. One is the high energy radiation. It takes 8 minutes, right? So the X-rays will take 8 minutes to reach here. Not much of a, unless you can predict the flare itself in advance. Once it has happened, you have 8 minutes, which is not much of a time. The solar energetic particles, which are related to both flares as well as acceleration in CME shocks, takes on the order of hours because it travels roughly 1/10 the speed of light. So it takes on the order of few hours to reach Earth. A coronal mass ejection, on the other hand, takes a few days. So a very fast storm will take 1 day. A slow storm will take about 3 days to arrive at Earth. The CMEs you can actually see happening as well, but you have a large window, longer window to make that, make that prediction of arrival time prediction. Flares, once it has happened, you have not much time. You don't have any time, literally, like you're gone, right? The energy particles take time. So if you're worried about flares, the best way is to actually predict the flares in advance itself. Not wait until you have observed them and then, okay, say, take evasive action. Not possible. Because 8 minutes, that's all that you get. Yeah, so I didn't talk about that at all today, but we also do machine learning, but I didn't talk about it because I wanted to stick to physics today. With machine learning models, you can actually predict solar flares. The CME models, there's no model which predicts CMEs. No AIML model, no physics-based models can predict CMEs. Flares, only AIML models can do, physical models cannot. CMEs, we haven't yet found anything that can predict the occurrence of CMEs. Much more complicated because it depends on the interaction of this magnetic loops in the active region with the coronal magnetic fields. Much more complicated to model. And coronal magnetic fields you don't see. So you don't have any observational constraint. You are really screwed. You are working with ghosts there, right? Literally.
So we need to wind up. We'll take the final question.
Yes.
Yeah.
So you showed a simulation of how the solar storms, it affects our magnetic field lines. So on the other side of the Earth, which is not facing the sun, the magnetic field lines are getting oriented in such a way that there could be chance of some sort of magnetic reconnection, probably.
Sorry?
There could be chance of some sort of magnetic.
There is a lot of magnetic reconnection going on the night side.
So can we expect some charged particles to?
Oh yeah, absolutely. So essentially, if you look at the simulation on the night side, there is a strong current sheet there, and that current sheet exists because of the forcing of the solar wind, actually. That current sheet also is highly dynamic, and so look at this side. So you have oppositely directed magnetic fields in this region in the night side, and that's called the magnetotail current sheet. And when you have a storm, and that simulation is up here, which is a CME hitting the magnetosphere, you will see the current sheet in the night side also display some dynamics. Let's go here. Yeah. So the night side would be here. Yeah, right there you'll be also seeing some dynamics happening. And you have charged particle acceleration in the magnetotail, which will then make its way throughout the magnetosphere and create what is known as substorms. Substorms follow the main storm and create a whole slew of stormy activity during the declining phase of a geomagnetic storm. And the magnetotail current sheet actually and charged particle acceleration there impacts that.
All right. Let's thank Dibyendu again for this illuminating talk. Thank you, Dibyendu. So please join us for tea in West Canteen.